So welcome to our, I guess this is the last and review class of Big Data Analytics. Last week, we had each of your project come up and sort of like discuss your data set and the sort of work program or sort of approach or methodology you would like to apply. And hopefully the feedback were useful. And you guys can go ahead and prepare your, I guess, video presentation. We'll link it up on YouTube and whatnot. It used to be where I had to use a separate program to record like a screenshot as I manipulate the screen, my mouse and whatnot. But now I think we can use Zoom to record. It's quite easy. Okay. And so you can mix that with your own sort of presentation flair, I guess. Okay, so have fun with it, but again, be short, be informative. Make sure that of course you start with the problem, then the data set, then the methodology, and then the results or sort of showcase or prototype what you got to do. Okay, so today being the final and review day, we'll do exactly that. Okay. Now, if you look at the class syllabus, we pretty much covered everything. Now, the difference being that I think last year I spent a bit more time on going over the mathematical background, with linear algebra and maybe a bit more of calculus and whatnot, just to make sure you understand the basic mathematics. This year I took those out, right? Instead, I had Kun Kong Kan, who's kind of my right-hand person, come in and give you a sort of like a collab experience. So you know what it's real, what it feels like to be quote unquote, a professional data scientist working with a Python pipeline. Okay. Okay, so today I have two things. We're going to do a wide sweep review. Hopefully this would some of the things will be obviously all ground, but it's good to go over the insights and also the sort of like the coding requirement of it. And if we have time, the second half I would show you some of the maybe like data analytics project that I had worked on in the past. So a lot of that is proprietary or it's for clients, so I can't show you the details. But some of the items I can certainly show you the gist of it. And there's also a lot of little project that I did for demonstration purpose, so you can look at that. Those are completely open to public. Okay. So, welcome to the review class. Now, again, this class is it went on in tandem with my developing this interactive textbook, right? It's a textbook that outlines a concept as well as gives you the code snippets that you can try. This morning, by the way, I had a sort of like a talk, introduction to AI and whatnot with a high school team. So I had the opportunity to show them a little bit about the modern way of working. The idea is that yes, you can very much learn the coding and mathematics at a very high level, so you can tell it what you want. But even that, sometimes the steps may be a little bit daunting. So you can literally ask ChatGPT to write a mathematical code first. It's not guaranteed to work, and it's not going to give you the parametric specificities that you like. Okay, but there's an example where I asked it to draw like a partial differential equation, solution to a partial differential equation with initial condition. It came up with very runnable, executable. So you can then take that and then adjust the parameter, adjust the function, and so forth to your liking. Okay, right. So let's go chapter by chapter again. Now, Let me squeeze all the chapter back. This book has 6 chapters. Okay. I actually have a code here that saves itself at the end, so we don't need that. Okay. Right. So this is kind of generic table that I used to write. Okay, so chapter 1. What does chapter 1 do? What does chapter 1 do? Okay, let's. I'm gonna collapse everything, and then maybe ask you a little bit more. Okay, that's about it. Okay, these are all. When you read a book, especially textbook, okay, and this is a hint. This is a hint. What you would like to do is test yourself on whether or not you can replicate the table of content. If you can actually replicate the table of content of a book in your mind, that means you have a good map of the subject content. Okay. Now, in the extreme case, what I can do is I can ask you on an exam, like, okay, this is a table of content. What is 1.3.1? And see if you got it. Okay, but that's a little bit too cruel. So I'm not going to do that. But here, so here, what did we do on the first day? First day was the concept of data, right? What's the most important thing about that? Okay, what's the most important thing about data itself, right? The concept of data, okay? We're going to do data analytics, but we have to say, what is the data itself? And then, you know, you have the notebook, so you can read it if you like. But the main concept is that data is supposed to represent the record. It's supposed to be a record that represents a sample of population. But your interest is not in that sample. Your interest is in the population to which that sample belongs. Okay? And you remember when we go to supervised machine learning with when you build a decision tree or neural network, you block data into 2 sets, right? There's a training test and a testing set, right? The training set is the data you train the model. But once you train the model, you're supposed to throw that away, right? Because you're not interested in the training sample, okay? The testing sample is the data on a general population that the model hasn't seen. So your concept is about, you know, generalization of sort. Okay. There was a fine point when it came to unsupervised learning. Remember, do I want to take the data set and then cluster it once and then draw insight from it? Or do I want to create a clustering tab so that when the new data set come in, I can say, okay, which cluster does it belong to? Okay, and what's the fine point associated with that? If the new data set is kind of large, you might as well, you know, redo the clustering, because it may well be that the new population represents a new mix. Okay, so it's like right now I do a clustering of this class. I've got 2 classes, right? If I have a new guy comes in, I can say, okay, where would this guy belong? This group or that group? But if I actually have 50 more students, maybe that 50 students will form a different cluster, or maybe would lead to different conclusion altogether. So, you know, I start with 50 students, I have 50 more students, I would probably be better off rerunning the clustering analysis. Okay, why? Because the first 50 set doesn't give you a good generalization power with respect to the other 50. Okay, but if I have just one more guy, yeah, maybe that's good. Okay, so these are sort of like fine issue about generalization that I hope you appreciate. Now, these are not like technical questions that I would you know be able to necessarily test you specifically on, but I want you to be aware of all that. So the issue of data, first of all, you have to understand that you're not interested in the data. You're interested in what it says, because hopefully data is drawn from representative example. Okay. Now, if you are willing to say this data set is representative, then by all means, you know, you have 50 more students, don't rerun it. Okay. The key idea is representativeness. And that's in a way it comes with professional experience as well to make that kind of judgment. Okay, and data analytics, of course, is just refer to any kind of quantitative tools that perform analysis on data, so that you turn data into information, turn information into insight, turn insight into better decision making, right? That could be commercial, that could be social impact, that could be whatever. Okay, so that's up to you. Now, the idea is, okay, we develop in this class set of analytics. And for the purpose of the class, as well as my book, I kind of organize into 3 groups, right? What are those? Those are, okay, the first group is basically the subject of chapter 3, right? Chapter 3, because chapter 2 is about mathematical code. So chapter 3 here is about what? Interactive visualization. So that means that if you allow the user to, probe different variable, look at this variable X versus that variable X versus this Y versus that Y versus this in different dimension, it gives you the right insight. Okay, there's no model built in it. Okay, you just, so that's this chapter 3. Okay, chapter 3. Okay, interactive visualization. Okay, what's the second group? Second group is very traditional, based on statistical models, right? And that would be chapter 4, probabilistic model. Okay, so this is based on some kind of assumption, and this is where that sampling thing means very precise. The population is normally distributed. You draw a sample of 30 cases, and then you make some inference about the mean of the population. Okay, it's very strict definition of sample and population, and it has a very nice statement about what the distribution is. You can do all kinds of tests. It's very powerful, okay? But you can't always use it. First of all, it's very rare that you would use this for text data, for example. There are, by the way, there are actually statistical model on text data, but nowadays you would just go to like large language models, okay? So those would be the second group, probabilistic statistics, right? Based on probability model, and then you do that. And then finally, the last group is based on machine learning. And this is where all the algorithm, whether or not it's, AI flavor or just very heuristic, like decision tree that doesn't look like an AI model, or neural network, that's the basis of all modern AI. That's where that comes in. So that's chapter, what? Chapter 5 for unsupervised model, and chapter 6 for supervised learning model. Okay, and remember from very day one that there's one major class of supervised of machine learning paradigm that I didn't cover in this class, and that's reinforcement learning, because it applies a lot less to data analytics. It applies more to robotics. Finally, both supervised and unsupervised learning on graph data is treated in a separate chapter in chapter 7. Okay, so now I'm going to quickly go through some of the things. I think what's useful is actually run through a little bit of this. Okay, so this chapter 2 here is introduction to Wolfram Mathematica. And again, Wolfram Mathematica is different from, say, general language like Python or C, in that it is symbolic, in a sense that you can even calculate with infinities, for example, right? And it's more declarative. You ask it to do something rather than you tell it what to do. So build me a classifier, as opposed to here are the steps. Okay, so it's more it's basically functional programming like Python, but it's more than that. It's a bit more. It takes on a declarative flavor. And the way the interface works is, again, it's by kernel, just line by line, because and some of you are used to that, because a Jupyter notebook in Python is actually a copy from Mathematica notebook kernel. And it's got a lot of interactivity things to it, okay? And finally, it's actually a very popular backend to ChatGPT, Okay. Now, how many of you have played with ChatGPT? How many of you have subscribed to ChatGPT Plus? That means you pay a little bit more money and it allows you to hook up to the back end. So that's a case I told you. Because I pay for ChatGPT Plus and it's hooked up to Mathematica. I said, please plot me a solution to partial differential equation that describes the heat dissipation. And then it would go to Mathematica and then plot it. Remember that. Okay. Now you don't have that. It doesn't go to Mathematica to do it for you if you just have a ChatGPT. But you can ask something more general, like write me a Python code. You can do that. It doesn't go to Python. You have to copy and paste, I think, if you don't pay for, if you don't have the hookup. I don't know. Okay. So concept of look again, these are all data. I'm just going to quickly jump over. Okay, and this is the Wolfram thing, Wolfram Alpha. And this is where you actually, it's more like Wikipedia Plus, right? And these are the example data. Now, I want you to start paying attention on the primitives. Okay, so the most important thing, again, this is not just Mathematica, but Python in particular, list. How do you handle lists? All right, list is very important concept. So I would advise you to do this because, like say in exam on your project, you have to do list. Now, list is like this, it's manually enumerated, right? And then you can access it and so forth. But one of the most useful, okay, it's not the list itself, but how do you construct it? Okay, the most useful way to do it is, what is it? Table, right? Table. So, yeah, table, and you can do any kind of stuff, right? You can say A subscript I or something, okay? U or I, whatever, I, comma, I, going from one, well, you don't have to start from one automatically, so something like this, okay? So this is going to give you, okay, right? Now, even though I haven't, delved much into Python, you should know the terminology. How would you do this in Python? List comprehension, right? Okay. Okay. So, function built in. So during the exam, what I might like to do is ask you to write a function. Okay. Now, built-in function like, let's say, A10 equal to this guy. Okay, so that's the previous guy, and length A10, right? So that just gives you 10, obviously, right? Now, what I want you to do is be able to write, show me that you can write a user-defined function. Okay, and okay, so take a note. Okay, you should be able to on the spot write a user-defined function. So my add A, B, right? This is kind of like a little bit moronic. A plus B, right? Right? So my add is nothing more than that. Just add two numbers together. But the idea is that you know that this is something that you are going to use many times. So obviously it's not going to be something this simple, right? And this is the variable reference and so forth. So what tends to happen is you have something that is also multiple line, okay? So I can have something like length, sum, okay? Now, if I have something local, okay, so first thing, okay, if you want to write down what you need to know, list, table, I'm giving you something specific, okay? User-defined function. Now, one of the things that's most useful is to hide variable from global scope. Local definition, how's that done? That's using module, right? So that's another thing that you should be able to do on the spot, module, right? So I'm going to define module as have a local variable sum, comma, okay? And then sum is equal to A, okay? And then sum plus equal to B, okay? Finish. And that's going to give you the sum. Or, if I want to be even fancier, you can close this and say return sum, okay? Okay, so now I can call the same thing, my add, I don't know, okay? What happened is it creates internally this value called sum, adds, sum has nothing. It starts with 111, add to it, and then return. The reason we do this, even though it's completely stupid, right, is because now you can do all kind of fancy stuff. Okay. Now, when you look through my code, you will see that sometimes, because I can start initialization right here, actually, make life. Okay, so remember this picture, just so that you have this structure sort of like imprinted in your mind. It's a function. It has external parameter or variable that we put in. It gives something back. It has internal variable that you can define. And if I ask for it later, doesn't know. Okay, fine. So that's module. Okay. Grid is a good way of organizing tables. So all this is in there. Okay, I encourage you to just go line by line and shift enter. Okay, now, so this is module and plot and all kind of stuff. So I'm not gonna, I just want to, I guess, walk down this. Okay, what's the second most important data structure beside table? Is association, right? Association. You can write association manually like this, okay? Or one of the most useful function I have is what? Association thread, right? So you have a list of keys and you have a list of values. So if say my key equal to A, okay, and B, okay, and then my value is equal to blue and red, okay, and my association is equal to association thread, my key, my values, okay. So now I can use my association with A. So that gives you B, right? Now, if you're given an association and you want to know what the key is, then you ask for it. Keys. That's my key. And that's my values. Okay, good. All right. So you have the list, which can then be nested to make matrix, to make tensor. You have association. That's it. That's it. Those are the two basic data structure you are ready to make a living. Okay. Now, of course, if you're going to be a professional data scientist, this kind of association, you would like to be able to do some kind of like kind of database search kind of thing. So that's why you have this thing called data set. Okay, it's a built-in function. It's equivalent to pandas in Python. Okay, so for a big project, you wouldn't just have key values association. You would actually refer to this as a data set. So you can do group by, say, go through the column that say population, and then go to the key that say country and adds only country that's in Southeast Asia, right? So data set, pandas, same thing. Okay, so that's I had a sort of like I keep revising my notion of what's the best use of your time in class. I think next year what I'm gonna do different is instead of taking you to collab, so with Gongan, I'm actually gonna go just one full class in either pandas or dataset. Okay, because that's something that I think if you know how to manipulate it, it's very useful. So that's what I have in mind for next year. Okay, good. So once you know table, you can table is accessed by position, right? Association is associated accessed by key. That's the difference. Okay. So it's nicer than table because if a table or a list, if I want to access you, I know that you must be element number 1. I want to access you, and I have to know that you're element number 2, right? But if it's an association, I give you a name. Okay. Good. Yeah. So association thread, make sure you know how to do that. I'm gonna literally ask that. Okay. Thread is also like a transpose, that's also good. So this area here, pay attention. Pay attention. Okay. And don't ask me what's going to be on exam. I'm giving you so much hint already. Okay. Now, blah, 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 blah. Okay. Pure function. Pure function is it as powerful as built-in function? No, because built-in function, you can write like 50 lines, right? Put in a bracket or whatever. So my function can look in, you can put in the module, you can say my function A, okay, is equal to, and then put in the bracket, okay? You can put in many, oh, sorry. Yeah. Yeah. And this here, this inside this bracket here, it could be 50 lines long. I don't care. Okay, it could be 50 lines long. Okay, a zillion lines long. But sometimes you don't want to do a zillion lines long. You want to do something simple like this, like add 2 numbers, okay? Or something funny like take the first element and then raise it to power of second element and divide by the third element. I don't know, okay? So those would be what? Those would be pure function, right? Pure function. So my pure function would look something like, say, they take the first element, okay? Now, the only thing I want right now, the reason I'm giving you this is I want to show you 2 versions of exactly the same thing. Okay, this here, take the first argument, okay, add to the second argument, okay, define it as what? As a pure function, right? And then I can apply it to, I don't know, A and B. Okay, A and B. Oops. I think I defined B somewhere. That's bad. Okay. Okay. Right? That's A and B. Now, what's the difference between this? Okay, so this here say argument number 1, argument number 2, add them together. That's what I want done. Take the first one, take the second one. Now, let me show you another version. There's only one argument. There's only one argument. There's only one argument. So I raise to the power 2. Okay, and I apply to A. So that's A to the power 2. Fine. Okay. Now, I'm going to do this. I'm going to use 2 things, A and B. But now it's one object. So what I'm going to do is take this object 1 plus, oops. Okay. And this does the same thing. Now, what's the difference between this and this? Okay. Okay. I want you to memorize this in your mind because this will help you so much. Again, I'm giving you something that looks stupid. Why you already know how to add A and B. Why would I do it in two different ways? Okay, that'll be situation. What's the first situation called for? The first situation say, I'm expecting two arguments. Take the first argument, add to the second argument, I'm done. What's the second line say? The second line say, I'm expecting one argument, but that argument is a list. I take the first element of the list, add to the second element of the list, and then I'm also done. Okay? Right? That's the difference. That's the difference. Okay? Now, and here's the question I would ask on the exam. Okay? I have a whole bunch of numbers to add together. Okay? I have a whole bunch of numbers together. So I have A and B that I want to add. I have C and D I want to add together. I have E and F I want to add together. So this is my, okay? And in theory, this list can be 1,000,000 pair long. Okay? I want to go one by one and add the component. I want to add A to B, C to D, E and F. How would I do that? Okay? I can define a built-in my add, okay? Or I can do this, right? And then I use map. Okay? Why don't I use this? I don't use this because this thing is expecting two things, not one thing. But let's try, see what happens. Let's see what happens, okay? No, doesn't work, right? Because it said, hey, this is my first thing, this is my second thing. What do you do? Okay? So this one would not work. So now I'm probably not going to ask you this exam question, which one would you choose? Because you can try both and see which one works and say that's the answer. So that's not a good exam question. But you see what I mean? This is the difference. I want you to understand this. And a lot of time I use this. And a lot of times so will you. Because what if you have a whole bunch of data, right? Now I didn't prepare data for this, but let's say this is my data string and this is another string, and what I want to do is normalize. Okay, I want to normalize every line. How would I do it? I would take the sum of each one and divide by the total, say. Okay, and I want to do this for all the lines, and I want to do it once, so I can do this sort of thing. So the thing you have to remember is this kind of pure function is handy. The keyword is handy. Built-in function and user-defined function are powerful. Can do a lot of things, can have 1,000 computation steps. But pure function, if you do 1,000 steps in pure function, you probably make an error somewhere. It's going to be terrible. Okay, you can do literally this. You can do something like, you know, you can use a bracket here. And then 1,000 more instruction, but you will probably break it somewhere. It wouldn't work. Okay, bad style. This is not a coding class, so you don't have to know that. But you need to know that, yes, I will actually, as a data scientist or data analytics, often want to do simple reformatting, simple calculation at once. Okay, and I don't need to do it again ever. Okay, so I'll just use pure function. So pure function, there'll be 1 or 2 questions on pure function. Okay. Again. For those of you in Python, these are called, I think, lambda function, right? I think, am I right? I think it's called lambda. Okay, now, finally, what are, so you have lists, okay? You have lists, you have this thing, which is something A to blue, B to red, or whatever, okay? So that's association, right? So that's it. You're ready to make a living, but for what? For supervised machine learning, you will learn of one more appearance, and that's something like this. X1, 0.2, Y1, X2, 0.2, Y2, right? Oftentimes, X1 is a vector, so you actually have something like this. Okay, right? Now, how would you do that? How would you do that? How would you create this? Okay, so again, these are the three things you have to be able to create on the spot on the exam. Okay, so if I have, say, something like I don't know, X so 2 and 3 and 4, and then 100, and then 2, 3 and 77, and then 200. Okay, that's it. Okay, that's my data set. Okay. Now, you're not going to get this data set that looks like this, right? Chances are you will have some data that looks like, okay, let me make it a little bit different. 4, 5, 4 and 8. Okay, so I will actually give you this tiny looking data set. This is my tiny data set. Okay, I'm gonna want this from you. I'm not gonna give it to you. I'm gonna give you this. And this is where your tabular data comes in. Right. This is the last chance. Something that I cover very quickly in class. You're gonna, okay. Because I noticed that I think during the midterm, some of you were struggling with some of the things that I thought was obvious, but not. Okay, so if this was my data, right? You look from CSV file, right? CSV file, it looks like this, right? The first row has 2, 3, 4, and 100. So X1, X2, X3, and the Y1, Y. And then you have the second row, and maybe you have a third row. Okay? Have a third row. Okay? And this row is something like, I don't know, 5, 7, 9, and then output is 350. Okay, so that's my data set, right? That's my data set. I in practice, you would say something like data is equal to import and then .csv or something. Okay, but I'll just give this to you as a mini data set. Now, I want you to build a function, right? That takes 2, 3, and 4 gives 100. 4, 4, 9 gives 200, and then 4, 5, 9 gives 350. How would I do that? So this is my data. Okay. What I want is this. Right? Why? Why do I want this? Why do I want this? Okay. So I'm going to call it data IO is equal to this. Okay. Why do I want this? Because now it's in a supervised learning format, right? So I can say my predictor, my F, is equal to predict PREDICT, and I put in data IO. Oops. Okay. And this is going to be a silly little thing, but there, you got a model, right? Now this model can be applied. You can say, okay, I have a new data set. It's not 2, 3, and 4, but it's 2.3 and 3.2 and 5. That's going to give you some value. Now, it's a terrible model, so it's not going to do anything good, okay? Right? So I give something that's bad. If, in fact, you know how bad it is? I give you exact same input, it's probably not going to get it right. Because this is, yeah, it's built something stupid. So it's not going to work. However, that's not your job, okay? Your job is not to build better algorithm. Your job is to use better algorithm to do your data analytics. So my question would be, if this was your data, how would you make it like that? How would you make it like that? Okay, I'll just do it quickly. Well, what you want is you want to thread, right? So we do that again. Data IO is equal to thread. This one is not association thread because I don't want an association. I want the thread. Okay. Right? So what I want to do is take the 3 columns. Right? 3 columns. So I'm going to say data. Okay. I want all row, right? So all, and then up to 3 columns. Right? And then I want it to point to data all. And the last column, which is column number 4 or -1, same thing. Right. See that? Okay. Now, on the exam, I can give you simple, data 3 line, or I can ask you to put in the student ID, generate 1,000 line. Let's say you have 1,000 line. Okay, I have 1,000 line. Okay, if I have 1,000 line, data is 1,000. My question then would be, how would you make training and test set out of it? Then you say take drop. Right? Take drop. Okay, for example, take drop, if you have 1,000 items, you can take the first 70% and then the other one. So take drop. Okay, so let's say I have well, let me just do this. Okay. What do you think is going to happen? Take drop just going to separate data into 2 chunks. The first data is a range of number from 1 to 100. I take the first 80, put in 1 chunk, right? And then I have 20 more. So now if I have this is my, so this one, the first one would be my training set. The second one would be test set, right? So how would I do this? I would say my train set, my test set, okay, is equal to, right? My train set is it data IO, take drop, okay, data IO. Now I only have 3, so the best I can do is 2. That's it, right? So what's my training set? My training set now consists of 2 samples. What's my test? 1. Right? So, and pre-pen, append, these are kind of like manipulate string. I'm not going to pay too much attention. Okay. Replace. I didn't go over that too much. Map, this is very useful. We use that all the time, but we use a shorthand version of it. So make sure you use that. Apply is useful. I'm going to skip that one, not so much. Data set, again, I didn't devote that much time in this class. So that's it. This is analytical. You don't need this because this is kind of like for something else. So skip. Well, you don't have to skip. You can enjoy that. Oh, by the way, this is the differential equation. This is the cool thing that I did for high school student. So build a differential equation and show that it works. But then you can also ask ChatGPT to build a differential equation, and it comes up very close to what I've got. Okay, it's very cool. Very, very cool. It's kind of good fun. Okay, now probability statistics. I think all of you are not doing. I think there was one guy who wanted to do it, but in the end just gave up. Probabilistic model, right? So I'm gonna ask maybe more probability model in the exam. Okay, right? How do you work with probability? Well, probability function is not something that you invented, right? Right? You go to Wikipedia page, remember that? Yeah. So, which distribution to use? Well, first of all, look at your data, okay? There are certain data that's bounded, certain data is finite. So there are 5 categories, right? You need to know this. You need to know this. There are 5 types of probability distribution. What's the first one? Finite, right? In other words, you can have finite output like a coin toss, head or tail, a dice, 1, 2, 3, 4, 5, 6, right? Number of students that in this class that got a scholarship. So that's 0 all the way to 50. Finite, okay? What else beyond finite? Nope, still discrete. You have to think discrete and continuous first, okay? Discrete, finite. Discrete, not finite, that is countable. Number of accidents, okay? And I only give you one thing to study, and that's Poisson, okay? So number of accidents, for those of you, is infinite, right? It could be 0, 1, 2, 3, there's no upper bound, okay? So finite, sorry, discrete, finite, discrete, infinite, or countable. Now you go to continuous, right? And continuous has 3 versions. Bounded, like uniform or beta, no smaller than 0, no bigger than 1. Semi-bounded, no smaller than 0, no bigger than infinity. So it goes all the way to infinity. And then unbounded. So bounded, semi-bounded, unbounded. These are the 5. Okay. For the name distribution that I underline, I'm not going to go over that here. Okay. I can ask you, okay, beta, what kind is it? You should know that. Okay, because I only gave you no more than 10, right? Remember? Poisson, what's Poisson? Countable, right? What is normal distribution? Goes to minus infinity to plus infinity. That's unbounded, right? What about gamma? What about gamma is semi-bounded? Uniform bounded. Okay? So these are knowledge that, yes, you can ask ChatGPT, but you're going to look really stupid if you go to an interview and they ask you and you don't know this. Okay? So you know, okay. So these are all these things are listed in the, don't remember. It would be in, I think, yeah, heading number 2. I'm getting ahead of myself. Okay. But then you have to do this thing about mean, variance, median, and all kind of stuff. So the thing that I was telling you, these are the guys that are down here, right? You start to go into distribution, family. There. Okay. So binomial. Okay, binomial. I'm definitely going to ask you something about binomial, I think. Why? Because binomial is one of those things that you can make a living from. Okay. These are lifetime probability. Again, there are about 100 known distribution that people have defined. In this book or in this note that you have, I only listed 10 because I'm telling you that those 10 you need to know. Okay, the other 20, the other 30, yeah, you will impress me if you knew, but you don't have to. I certainly don't. I never needed to impress anyone. So, okay, but you need to know this 10, okay? Because if you did, okay, this is now something that I would love for you to know, okay, but I don't expect you to, and I'm not going to ask, is how different distribution names are related to one another. For example, if gamma is a general form, Erlang is a specialized form of gamma. So these are something that I would go deeply into, probability statistics class. I'm not going to ask you any of those. However, you will notice for your own use that if one is a special case of another, in this notebook, you find them in the same place. Good example would be uniform is a special case of beta. So that's why you see something like this. Okay. So that's beta. But if you choose the right parameter, okay, 1 and 1. I can't see right now. It's not in my head. I don't know. Oh, a divided by a, so 1. So this has to be 2. If I choose this to be 2, and I choose this to be 0.5. Okay, now I get uniform distribution. Okay, so what's a special case of that? I'm not asking you to know this, but you can see that when I say this is a special case of this, for your future use. Okay, here's a good one. Exponential Erlang is a special case of gamma. Okay, so I don't list them separately. Okay, just so you know. Okay, chi-square, log normal. Okay, fine. So these are the things that you can play with, and normal is the most special distribution of all. Okay, you're not in a probability class, so I won't expect you to know details about central limit theorem, but it is important. That's why you put up with it, even though it's it's messy to write down the code. Okay, popular, you can skip that section because you're not part of that thing. Now, this is where I would ask you to find. So what I would do is you put in your student ID, right? That's going to randomize some data set. And then based on that data set, you can look at it. And you can see that maybe it's discrete or it's continuous in value. It has negative, it has positive. So you decide which one parameter to fit. Let's say you got this data set and it's continuous, right? Now, here comes my question. Okay, my question. First of all, let's say, okay, I'm just going to make a real case of this then. So based on some randomization, data is equal random variant. Okay, and I'm going to make this up. Gamma distribution and 3 and 4. Okay, and 1,000, 10,000. Okay, I'm just going to do this. Okay. Now, you won't see this. You won't see this, right? But you can certainly do this histogram. Okay? Okay? With this histogram, you can see, and you can look at a few data sets. You can say, oh, data, and let's look at the first 10 of them. Oops. So it's kind of decimal. So, you can kind of assume it's continuous. It's continuous, right? It goes no less than 0. It goes all the way somewhere up. So what would you think this would be? This looks like a semi-bounded. Semi-bounded, okay? Now, you've only learned 2 semi-bounded. One is log normal and one is gamma, okay? So let's say you're going to make a guess, okay? How would you do this? How would you fit this distribution? You would then estimate it, distribution, right? And then gamma, distribution, and then A and B, and then go to the data, my data. Okay, sorry, I put it up there, right? So this is my data. I'm going to guess it's gamma distribution, and this is by A and B. So my answer would be, what are the parameters? It's going to be 3.05 and 3.95. Now, how do I know that this is correct? Because I actually generated with 3 and 4. Okay, now you can make wrong guess. Okay, so let me show you again. You can make wrong guess, but as long as it's sensible. For example, you can do this. You can guess it is log normal. Okay, this is a wrong guess, but you get a full mark. Why would you get a full mark? Because you didn't know what the right answer is, but you choose one of the right distribution, right? Right? So am I going to punish you for that? No. Because in reality, this one is part of nature. It's generated from nature. Nobody knows the right answer. So this answer is just as good as that answer. Now, what's not good is if you did this. Normal distribution. That's not good. You get no point for that. Why? Because normal distribution is unbounded. Right? Okay? So obviously this data set minimum is, it's always positive. Now you can check and all that. I can be mean and make a histogram that looks like this, but actually go negative, but I'm not going to do that. Okay. So this is a kind of flow I want you to be able to reason. You get a data set, you look at the 5 types, you decide. Okay. And then you fit. Now, this is a full mark. This is a full mark, even though I know that based on your random number generation, this is what it came out. Okay, but this is a full mark. Yeah, something like that. So this kind of inferential start with, distribution, mixture distribution. I did mention, but it's going to be a bit difficult, right? So for example, we have multimodal. You can say it's like 50% here and 50% there, or 30% here, 70% there. This is a little bit too much. Okay. But you know what? Let me tell you this. It turns out when I asked Mathematica to look at real world data, and I wanted to search, for an arbitrary class of distribution. Okay. Sometimes what I do is use this, find distribution. So I don't have to make the guess. Now I'm making you make the guess because you should know probability, right? But let's say you have no idea and it doesn't look like anything. you can use find distribution. So this one, find distribution data. Okay. Oops, did I just delete it? Oh, okay. See, it came up with gamma distribution. But I'm going to tell you what happened in real life. In real life, so many times when I did this, it gives you what's called mixture distribution. So it's like you take one gamma distribution, you take log normal distribution, you add 3 parts of this and 1 part of that. That's what mixture distribution is. That is so useful in real life. That is so useful in real life because a lot of real data is not nicely distributed. Okay, I'm just giving you that from experience. But so a lot of time I show in any kind of data, it's going to come up. Well, let me show you. Well, I know that this is going to be this is going to be multimodal. So I'm just going to do this. Okay. Join this one with okay, again, just because this is a review class, it doesn't mean I can't give you something new. So watch this. I'm going to do something else. I'm going to give you something like 10 and I don't know, 20. Okay. And I give you 50 of them. Okay. So I joined 2 gamma distribution. Now I joined it in such a way that there is twice as many the first kind as the second one. Now, what happened when I hopefully I don't get embarrassed here, find distribution. Now, I can use estimated distribution. Okay, let's do the right thing first. Well, let's not do the right thing. Let's do the wrong thing first. Let's say I have no idea. So I ask the Mathematica to come up with it. Okay, it's going to take a while because, 15,000 points, fine. See that? It comes up pretty good. See, it's a mixture, 67% of this, 32% of that. Hey, that's pretty good, right? Right? Because 10,000 out of 15,000, that's about 67%. And what's the parameter? 3.2 and 3.8. That's pretty close to 3 and 4. What's the second parameter? Close to 10, close to 20. Okay. Now, of course, I can be a bit more scientific. I can do this. Estimated distribution data, comma, and then I do mixture distribution A and B, gamma distribution C, D, E, F. Okay, and it gives you this as well. Now, obviously, why would you do this if you can just do find distribution? In real life, if the data is so huge and you don't give it an initial insight, it won't give you good results. Okay, and also it might give you something weird. And this is another thing. I have done this exercise again in real life, in real application, and it comes up with some kind of distribution which is very esoteric. Alpha stable distribution or something like that, which is not going to sit well with my client. When I say, okay, this is your distribution, looks like this. What? Okay, so I'm going to say, okay, well, my client can understand log normal because they went to finance school. So what I'm going to do is, tell you what, I'm going to make sure that even though I can find the right, a better fit this way by find distribution, I'm going to say, okay, my client only understand log normal. Okay, so I'm going to do this. I'm going to force it. Okay, because financial people, they understand log normal distribution really well. Okay, okay, so it's a log normal distribution. So let's say my client doesn't understand gamma distribution. I give you that, then they're going to get confused. Okay, so there's a lot of art and science in how you do this as a professional. Okay, you guys are not yet professional. That's okay. Okay, I'm just sharing with you what works. So that's why it sounds stupid. If you can ask Mathematica to do this for you, why would you do that? Well, here's why. Okay. So something like that. Kolmogorov, Smirnov test, that's kind of testing distribution fit. I didn't cover it in this class, so I'm not going to ask you. Now, let's go to the part of unsupervised learning. Okay, unsupervised machine learning. What are the two classes unsupervised learning technique that you have? Again, if you don't know this, you shouldn't pass. There's only two classes that I taught, right? Two things. You either find the data set and you find cluster, who stays with whom, right? Or the data is in high dimension. I want to reduce it in a lower dimension, hopefully 2 or 3, in such a way that if two data points are close in high dimension, they stay close in lower dimension, right? So those are the two, right? And in fact, that's pretty much, you know, that you can make a living out of those two, okay? So cluster analysis and dimensionality reduction, okay? Now, when we go to graph data, I taught you more than this, right? What else did I give you? Centrality analysis. That's also unsupervised learning. Okay, but that's graph data. I'm talking about just regular tabular data. There are only two techniques, two classes of techniques, and they're huge. So one is, okay, clustering. One is dimensionally reduction. Now, dimensionally reduction, I taught you, I think, just the linear one, principal component analysis. But the popular one, if you go on in machine learning, there's t-SNE, there's UMAP, there's all kind of stuff. It's all in here. So you can follow through that. Let's see, you know, it's in. Okay, let me collapse some of this. But first, okay, so first, cluster analysis. Okay, once again, if you're going to do it once, what function are you going to use? Find cluster. Right? If you're going to do it not just once, but keep that clustering later, you're going to use cluster classify. Okay? Again, these are simple, lazy kind of like question that I can ask because it's easy to grade, by the way, if you see it, you can look and say, okay, I say, I have a data set. I want to do clustering analysis just on this data set. Okay. But it's possible that I'll have, you know, a few more guys come in and I want to fit a few more guys in the existing cluster. What would I use? A, find cluster. B, cluster classify. The right answer is cluster classify, right? Because when I learn it, I can map it later. Good. I have 50 data points. Okay, 50 data points. I know tomorrow I'm going to get 500 more. Okay, what do you think would be the right game plan? Well, today I've got 50. I'm going to find cluster for the 50, but tomorrow I've got 500 more. Chances are I can't really think that 50 is going to represent 500. So I'm going to add the 500 tomorrow to the 50 today, get 550, and do it again, right? Find cluster again. Because I don't believe that 50% I can do cluster classify, learn the mapping, and then it's going to apply for another 500. That doesn't make sense. Okay. Again, these are not hard and fast rule, but it's a good way of reasoning. Okay. And if you did this kind of reasoning, nobody's going to say, oh, you did a bad job. But unsupervised learning has no right or wrong answer. Okay. Right. We'll leave it to chapter 6 when you have right and wrong answer. Okay. So you can learn the partition, use it later, or you can do it once. And clustering method. Now, I have to apologize a little bit, but I decided to go in a little bit more detail. So the classification of clustering method is slightly different from when we covered the class, but you know. So this thing is called hierarchical branching. So this is the dendrogram. That's, you use something like this. This is a dendrogram. So that actually it's not, technically it's not quite clustering because it actually goes to individual data point. So I call it branching. Okay. So in the original node may have been called clustering, but it's actually just branching. It branched all the way to individual data point. So obviously this is not going to work for 5 million data point. Okay. But if I have, 200 colors here, 100 colors here, I can certainly use, right, a dendrogram or clustering tree. Okay. And this goes to individual point. Okay. Now, is this clustering? No, but if you draw your finger around it, it is a cluster, right? But it's not a clustering technically. Fine. So that's branching, hierarchical branching, two techniques. Now, these are the two things I want you to learn. One is distance-based and one's density-based. Distance-based means you're close together, right? Okay. And what if you're far apart, but somehow there's like a river separating the two? You would go for density. Okay. Now, the distance-based parameter and density. Okay. Then there's a mixture model-based. That's I'm not going to talk about it. Okay. So basically, you need to know this guy, DB scan and k-means. Okay. Just know these two. Maydoi is similar to that enough that you can read on it later, but definitely DB scan and k-means. Now, Gaussian mixture is technically both a model based because it's based on a Gaussian model, as well as, density based. So Gaussian mixture is also very good. Mean shift is good, but I think if you want to go in an interview and they ask you to give an example and you don't know DB scan, it's going to look embarrassing. So that's why I say, okay, DB scan first. K-means, okay. Now you won't embarrass us. Yeah. But Gaussian mixture, it shows up quite a bit. Jarvis Patrick, I'm not going to tell you what it is, but it's awesome like that. So these are the example, and I think we did example on, I generated 3D, 4D, all kind of stuff. Now, what you can use for your, I think some of you are already copying this code for the project. So I won't have to cover that, right? So this is the analytic pipelines, right? Do the clustering and all that. First, visualize clustering. Okay. This one is k-means and yeah, so blah, blah, blah. So this is captured as a function. Okay, I'm not going to go over this again. Okay, but once again, you have to say, yeah, I have to be able to answer this. This is my output. What did I do? Yeah, obviously, you did clustering. What else did you do? You make the thickness proportional to cluster size, right? Because this is actually thickness. So there's more people here than there. I think this is a country. Okay, right? So if you look at individual, it's it's just one. But now you have two. How many clusters there are? 3. Okay. Now in this case, I happen to say I use k-means method with 3 means, three cluster. And what else do? I use radial axis plot. Okay. If you write the word cobweb or spider, it's okay. Some people write like that. I don't use that. So I used to call it cobweb a lot because again, I came from industry, and in the business they like to use the word cobweb. I say radial axis plot. They go, oh, what? Okay. But now I'm an academic. I'm just going to use the proper term. So I don't use cobweb anymore. So, I mean, you have to have a very symmetric spider to make this. Okay. So it's not a cobweb. I call it radial axis plot. Okay. Good. Now, conversely, instead of asking you what I did, I can ask you conclusion drawn from this. And this is almost like interactive visualization, right? Except you did more than that. You did the unsupervised learning. But imagine that you got this. What's your insight? There are, 2 chunks of countries. This is a big chunk of country, and this is another big chunk of country, and a small chunk of country, small chunk of country, small chunk of country, and there's a small chunk of country that has very high value of this thing. Okay, so this is how they distinguish. So this obviously is based on centroid. So the fourth step to make this cluster analysis, partition the points. Each cluster find the centroid. Each cluster find how many there are. Plot the centroid on the radial axis plot with thickness proportional to cluster size. Right? And in fact, again, I'm glad to see that many of you are copying this code to use in your project. So now this is dimensionality reduction, and by the way, I can also in a more sort of like fancy version, I take this data set and I can show you the cluster, the centroid, right? What else can I do? I can also reduce the 12th dimension into 2 dimension. Then I can plot all the country with list plot, sorry. Each cluster would have its own color. Does that make sense? Okay. In fact, I think the original version I gave you was the full version. I shouldn't, that might confuse you. But anyway, so there could be another plot here that does the, so this will be clustering analysis. If I want to do clustering analysis, but I also want to visualize individual country. Yeah, I can't visualize individual country in all 12 dimensions. What is my option? Well, I can say create an interactive plot, choose 2 dimensions at a time. That's a nice way of doing things, right? So I can say I take the infection rate and diabetes. Okay, x-axis is infection rate, y-axis is diabetes, and I plot all the country. I can actually put the name of the country on those plots, right? And based on the cluster membership, I can use the blue for the countries, red, green, and purple, okay, to represent the different clustering. And in fact, chances are you would see a bunch of blues together, bunch of red together, bunch of green together, right? Would you expect to see that? Actually, you would not. You know why? Because clustering is in 12 dimensions. When you put just 2 dimensions, chances are you're not going to see that nice cluster. However, if instead of plotting this one and that one, you take the 12 dimension, reduce it to 2, then you will see the blues together, the red together, the green together, the yellow together, the purple together. Unfortunately, what's the downside of doing it that way? You can't read the value of the axis because it's artificial, right? So if you find Thailand, you can say Thailand is close to Singapore and Bolivia with respect to the 12th dimension, but you can't read the value. So a professional way of doing this, I would have maybe 3 screens. Okay, one screen would be this. Another screen would be 2 reduced dimension. Then another screen would say, pick any dimension you like and show it. And that would be my analytics for World Health Organization. Okay, something like that. Okay, fine. And that would be a nice project as well. So, skip this. Okay. So right now, let's go to supervised learning. For the purpose of this class, yeah, I may have done this in maybe even class 1 because some of you knows what the regression equation is. But I think I might as well repeat the comment if I haven't said it. Okay. This is a good thing to review what you learned. Okay, do you know how? So these are the data points, right? These are data points you're given. Okay, you can do linear regression, right? Everybody can do linear regression. Okay, what's a linear regression? You fit a line to the point that minimize the distance from the line. Okay, so I'm gonna do that right now. Okay, oops, overshot. I keep overshooting the darn thing. Come on. Okay, play around with it. Okay, oops. I had it. Come on. A little more. You're right. On the left. Okay, it's not. Oh, I didn't know what happened. There's a delay. So, I got the right answer. Okay, so that's it. That's linear regression, right? That's a linear regression. Now, why is this not machine learning? This is not machine learning because in linear regression, you have a formula for the coefficient. You have formula for the intercept. You have formula for the slope. So you take the data, you put it in, you calculate one value, that's the intercept. You calculate another value, that's the slope, and you're done. Okay? So you get the right answer right away. But imagine that these two things, this intercept and slope, is given along this function. This is a function, okay? So this is intercept, this is the slope, and this is an error surface. Imagine that you don't get the right answer right away. You start with the wrong answer and you keep moving until you get the one that minimizes the error. If you did it that way, linear regression is a supervised learning algorithm. Okay. The reason it's not a supervised learning algorithm is because for something so simple as linear fit, there's an optimal solution for it. You can look it up in the statistics book, right? Now, you can also do nonlinear fit. So, the data is nonlinear, all kind of stuff. Doesn't matter. Okay. The point is, in statistics, if you get the right function, you get right away. Perfect. In reality, this is never your life. Okay, your life is always more difficult than this. First of all, it's not just going to be y as a function of x, it's going to be y as a function of 50 x's. Okay, so if 50 x's has 50 coefficient, then you don't have this 2D plane to serve. You have so many. Okay, so that's why machine learning is an algorithm. It starts out with a guess, and then it keeps guessing better and better and better and better and better and better until you minimize the error. Okay. So I use this, by the way, I intend to use this for essentially high school students, because high school students have done linear regression, and I want to say, okay, you're familiar with linear regression, right? Okay, think of it as an algorithm. But of course, we go more than that. Yeah, we go more than that. Next thing we go is well, we have to define two types of regression problem, right? One is kind of like numerical or continuous value. The other one is more like labeling. Okay. Now, what are the two words that I use? Prediction and classification. Okay, prediction and classification. But the word prediction, sometimes you can use the word regression. You can use nonlinear regression. You can use forecast. right? Classification, you can only use that one word. However, if you talk to a friend in biology department, what you're doing in classification in biology is called identification, right? Because classification for biology is like unsupervised learning. It's like clustering. Okay, good. Anyway, so let's not have debate about the name. So those are the two, and basically just the output is a categorical number or ordinal and nominal. Okay, so right away I can ask you again one of those easy to grade questions. If your output is a nominal scale variable, your y is nominal scale variable, would you use classify or would you use predict? Right? If your output is an interval scale variable, would you use classify or would you use predict? Okay. Again, your job is not to come up with kick-ass classification algorithm. Leave that to machine learning researcher. Okay. Your job is to make sure you know what to use, right? Because definitely very distinct. So logistic regression, for example, is used for binary classification. Oh, there's another word you might use, discriminant analysis. But if you haven't heard it by now, it's okay. You can live without. Just use the word classification for the rest of your life. Now, so this, I separate algorithm by what I call tree base and neuron base. And there's also a way of putting them together. So, this is basically tree base just has that. If the variable is between here and there, I go here, if there. So it's kind of like if then, if then, if then. And this is where I asked Gongkan to come show you, right? He showed you the decision tree, right? So that would be an example of a tree-based supervised learning algorithm. Okay? It's good for what? It's good for classification. You can use that for regression prediction as well, but most of the time you use the classification. After all, when you make the tree, it goes down to discrete class, right? So a perfect way of thinking this would be to think of the iris problem. That iris data is a perfect way of thinking about decision tree. If the length of the petal is between here and there, if the length of the sepal is between here and there, blah, blah, blah. And then, did Gongkan show you that tree? Yeah. Yeah. So each tree would ask question about petal width or length or whatever. And after a while, just say, okay, it's going to be this variety, that variety. And again, I've used it professionally, not because it's the most accurate, but it's also a very nice way of explaining. Okay, your client doesn't want this good model. He wants a model to be explainable as much as you can. So if a neural network, and I keep saying this, and I might repeat it. If you have a neural network and the decision tree model, and the neural network is much more accurate, which one would you use? You use the neural network. If they are similar in accuracy, again, testing, which one would you probably be better off using? That would be decision tree, because it's kind of nice to look at. Okay, explain, right? Because neural network, how are you going to explain? Well, you know what? What happened is we have a vector of number, you multiply by this weight matrix, and then you pass to this sigmoid function, you multiply by another set of weight matrix, and blah, blah, blah. In the end, you get the result. And that's a terrible way of explaining, okay? But if you say, okay, if this petal width, so this is something like, say, in your client data, maybe if the client is female, if the client is aging population from Thailand or blah, 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 then he or she is likely to buy this product. It's very nice to explain, okay? Composite supervised machine learning, I used to bunch this together, I separated. This is kind of like putting a whole bunch of things together. So if you have a decision tree, that's one. If you have 2 decision tree, 3 decision tree, 4 decision tree, you have 100 decision tree, you might as well call it a forest. Okay, so things like random forest. Okay, so this is under what's called boosting and backing. Okay, so kind of boost performance of simple things. But yeah, so how would you work? And this goes back to what I was showing you earlier, right? Have your data set, prepare it into input-output form, all right? Chop off some of it, set aside for testing, and then maybe 80 or 70% of it for training. I didn't teach you about info validation, but you should do that in real life, but it's good enough. I'm just going to say take 80% to train, 20% to test. Okay, for this class, that's good enough. Sometimes you separate into 3 classes, but that's again not too much here. So I have 2 examples here. One is FX, return prediction, and the other one is classification, right? In this case, classification, I think I use I use iris data. Okay, again, it's classic. Now, once again, it's a one-liner. Okay, you can specify method or don't specify the method. So I show that. Now, this is what I'm really going to ask on the exam. Because they require different way of assessing, right? So correctness or accuracy for prediction, that would be numerical. Okay? So you would look at things like this. Okay? This is good. What is this? Okay? This is a bad model. Why is it a bad model? Because actual value is between here and here, and prediction, they just predict one number. Okay, it's a terrible value. What is a perfect fit, guys? 45 degree, right? Right? Okay, so think 45 degree. Okay, but it's a continuous 45 degree. Now, what happens when you go to classification? You also want 45 degree, but in the form of confusion matrix. This is also 45 degree, except, by tradition, it goes this way. So the same thing here. If it's all over the place, so a bad model would be, so this is actual, right? Actual. And this is prediction, okay? The model would get it wrong, so we get a lot of off diagonal. Sometimes the model would just predict one value. Bad, they're all bad. What's a good model? All on the diagonal. So even though these 2 cases are depicting different situations, there's a good reason why I pick them. Because this shows a terrible model. There's no way you can predict FX return using 5 days. So this is a terrible model. Accuracy is terrible. Ask for everything is terrible. This thing is almost perfect because the data is simple. Okay. Right? Again, diagonal, training, testing. Now, here's a question. If you can only have one picture, would you show the picture to the left or show picture to the right? Well, if you're cheating, you show picture to the left because the picture on the left is always better than picture on the right. But if you're honest, you're going to show picture on the right, right? Because that is the testing data. Test. See that? You know what test, right? So in training data, 100% correct. Testing data, 1 error. Still pretty good. Okay. So this is based on like 20% hold down. This thing I didn't teach you. I kind of regret a little bit because this is actually quite ubiquitous. It's called receiver operating characteristic. It's basically saying that, if you're going to make classification, how your correct prediction versus correct classification versus wrong classification grows as you relax the criteria. Okay, this is a perfect. Now, I'm not gonna, since I didn't teach you this in class, I'll just give you, okay? A good model would fill up this. A random model would go on the 45 degrees. So 45 degrees correspond to random. Okay. Now you can get worse than random, so below 45 degrees. This is our ROC curve. Okay. This ROC curve is the one thing that I regret not showing you during class. Okay. This thing I also regret, but not so much. This is what's called SHAP analysis. This is sort of like, you remember with regression analysis, it doesn't do much. It's not that powerful, but what's good about it is you can explain it. You say, of the 10 variables, these are the 5 that has the most statistically significant coefficient. And that coefficient is very strong, positive, negative. Well, with machine learning, you can't do that. You can't do that. This SHAP analysis is a way of making up for it by trying to say, okay, this factor number 1 is pushing strongly. You get a lot of information from X1. You get not so much from X2. Okay. So this is something that I think in the machine learning class, or maybe even future data analytics class, it's going to be very important. Okay. So this, how would this be used, for example? Well, remember I told you that if I have a good model, equally good decision tree and neural network, I would use decision tree, right? What if I have a neural network that works well, decision tree that's terrible? I'm going to give neural network, right? Well, I can't give the coefficient of neural network because there are 50,000 coefficients in a neural network model. What I can do is say, you know, for this neural network model, if the input is female, chances are that's why the reason is this way. The reason we recommended this product is mostly because the input focus on the sex. Or the reason I promote this product is because the input pays attention to the age group. Okay, something like that. Okay, so it could be that for, I don't know, medical insurance product, age group matters a lot. So you see that the older it is, the more I'm able to push this health-related products or something like that. It's kind of indirect way of saying how it works. Okay, it doesn't tell you the coefficient, but it says this model looks at what. Now, I haven't, in machine learning class, you're gonna do things like pattern recognition, right? Like look at picture and say it's a cat. You can do similar thing. You know how it's done? There'll be like a picture of cats and dogs, right? And then the neural network will identify as cats and dogs. But you can also do this kind of thing, analysis, and ask the neural network what area of the screen makes you say it's a cat or a dog, right? And chances are it's going to focus on the eyes and maybe on the whiskers part. So the body part, maybe not so much because cats and dogs have furry bodies, right? By the way, this is very real story. There was application where you try, I think Washington State or something. I think their mascot is a wolf. I think, I'm not quite sure. Anyway, so what they want to do is do a pattern recognition to recognize a wolf, so that when the people walk in and you see a wolf, you know that it's a mascot. Let's say, okay, a mascot looks like a wolf. So what? And you have a dog come in, that's not a mascot, right? So go in somewhere, the dog goes this way, a wolf go that way. Let's say. So they wanted to do what's called a dog-wolf discrimination. Okay, so show a picture of an animal. Okay, let's get about cats and dogs. Say dog versus wolf, and this model is perfect. Well, not perfect. It's very good. But you know what happened? You know what happened? They do this kind of analysis. Ask the neural network in making the judgment that this is a wolf. What picture? What area of the picture it's looking at? Okay. And it turns out when you show the training picture, it's not looking at the dog at all. It's looking at the snow, because dogs don't get out in the snow as much as wolves. Okay, so when the algorithm perfect, why? Because most of the time when you have picture of wolf, you take it with picture of the snow, right? Right? Okay, because when it doesn't snow, you can't take picture of wolf. You can't see them. You can only see them in snow. So all the pictures on the internet that has wolf, most of them have snow. Dogs, on the other hand, rarely goes out in the snow. So most of the picture from the internet that has dog has no snow. So you train the dog versus wolf, and the convolutional neural network looks at the snow. This is a real story. This is not, I'm not making this joke up. Okay? It's a real story using this kind of analysis. But that doesn't happen anymore because people are smart now. But this is like 2015, let's say, when convolutional neural network was gaining traction and people were using it everywhere. And it turns out, yeah, they were looking at snow. It's kind of silly. Okay, so this is same thing, except this is looking for classification of 3 flowers type. So it has 3 different outputs. Finally, graph analytics on data. Now, this part has 2 sections. One is actually 3 sections. One is to say, I'm going to introduce concept of graph because scalar, vector, matrix. You add more depth, you get a tensor, right? Actually, tensor can keep going. You can have 3-axis tensor, you can have 4-axis tensor. So, I can't think of a good example, but the row, that's one. Column, that's another dimensionality. The color, that's another dimensionality. Maybe you add the smell. Maybe in the future, you can smell the screen. I don't know. Okay? Right. So anyway, the concept, and this is where I'm going to ask, as if I'm asking a mathematical question, but it's really understanding data. Okay? So, how would you classify, how would you represent graph data? Actually, you remember that input, output? Well, instead of input, output, you just have arrow pointing between entities, right? So this is one way of doing it. Okay. Bob knows Jane, and then Jane knows, I don't know, Irene. Okay, something like that, right? So let's say this is a graph plot. Okay, now it doesn't have a name. Okay, now, things you definitely need to know is what is the word, right? This circle thing, what is it called? Vertex, right? Label. It's automatic because I don't care. Yeah, before I plot the graph, I have to make it into graph first. Yep. Oh. Actually, it knows it's a graph. What happened is I put the bracket in the wrong place. This should work. Okay. See? Graph plot. Okay. Bob knows Jane, Jane knows Irene, and so forth, right? Now, in this example, actually, you want directed edge between Bob. Okay, technically, this is what you want. Bob and Jane. Okay. So, but I'm not going to hold you to it. There's a little bit of a. You see the head there? There's a big thing to indicate that it's a graph. So that gives you an arrow. Okay. But don't worry, use ordinary arrow. But if you use ordinary arrow, it may not show very well. Doesn't matter. Okay, fine. Now, what happened is, if this is the data set, okay, right? You can do that. On the other hand, okay, this is kind of hard to store. Where's the delete? Okay, so sometime what you would have is actually this: Bob, Jane, Irene, and then adjacency matrix. Okay, so if I give you this, okay, you should be able to tell me what the adjacency matrix looks like. So in this case, let's say Bob, Jane, and Irene. Bob is number 1, Jane is number 2, and Irene is number 3. Okay, so this is actually what it would look like. Okay. See? Now, how did it know this? Because Bob comes first, it's assigned the first guy. The next name it sees is Jane, so that's number 2, and Irene is the last one. That explains the automatic ordering. Okay, so Bob is 1, Jane is 2, Irene is 3. Because Bob knows Jane, 1 points to 2. Because Jane knows Irene, 2 points to 3. Okay. Now, in the note, you see a lot of things about symmetry and all that. Well, let me ask you this question. Is this matrix symmetric? It's not, right? Okay. So, right away, if you see asymmetric matrix, you pretty much know that you're talking about directed graph. Okay? But if you see symmetric matrix, okay, let me see. If you see a symmetric matrix, let's say you see 1, 1, and 1, 1 here, that means Bob knows Jane, Jane knows Bob, right? Technically, that could be 2 things. Either the graph is not directed, in other words, it's a relationship that has no arrow, or it is a directed graph. It just happens that the arrow, there are 2 arrows for every pair. Okay, so that happens to be the case as well. But anyway, so things like, so I can ask you something like Facebook adjacency matrix. Is that of friends, okay? Facebook friends. A network of 20 friends, or a list of 100 people. Okay, if they know each other, there's a connection. If they don't know each other, if they're not friends, they're not related. Is this graph directed or undirected? You can say it's undirected because if 2 people are friends, it doesn't matter who initiates. Now, maybe Facebook keeps a deeper record and say these people know each other, but A is the one who invited B, so there's asymmetry is broken. Symmetry is broken, right? But let's say just the Facebook network itself, who's friend with whom? That's completely undirected, symmetric. Okay. Now I ask you another question. What about following on Twitter? That's definitely directed, right? Because you can follow a superstar or Korean, whatever, God knows what, boy band, girl band, but they're definitely not going to follow you. Okay. Now I think Facebook also has follow feature, right? Now the thing is, I don't follow, so I don't know. I rarely even use Facebook. Okay. But Facebook is very good because, you know, when somebody dies, that's how you learn. Okay, so this is what the graph data. So graph data is actually a list of entities with connection, right? However, you can use, if I want to save this on a CSV file, That's not going to work, right? But I can certainly save this. Okay. So what's going to happen is going to say Bob, Jane, Irene, 010 001 000. Okay. Now, obviously, Bob can know himself as well. In this case, you can say something like, that's okay. That happens because, again, right? Bob knows Bob. Okay. Why would you see something like that? By the way, this thing here, okay, is data. Okay. But this thing that you see, a lot of time you will see it under what's called Markov chain. So it's like, instead of Bob, Jane, and Irene, you can think of it as happy, sad, and maybe suicidal, something like that. Okay. And this line here, instead of having just a line, it can actually have probability. So this is kind of like probability that you're happy today, you'll be happy tomorrow. Okay. You're happy today, this is probability you'll be happy tomorrow. You're happy today, this is a probability you'll be sad tomorrow. If you're sad today, this is a probability you'll be very miserable and about to kill yourself tomorrow. Okay. And there's also like absorbing state. You know, if you do this enough time, everybody ends up miserable because you can see how the arrow works, right? You can start here, you can end up here, but sooner or later, you're going to keep going down. So everybody ends up suicidal. So this is not a good example. Okay. But certainly if you have arrow going backward and you have probability, and so I didn't cover that, but just so you know, this thing is very useful in analytics. Okay. It's called Markov chain. In fact, I put it in here because I think I'm going to add it as a content. I keep adding content. So every time I add something, because I think it's so good, I have to say, I have to take something out. Okay. Or speak faster. Maybe I'll do that. Okay. Right. So these are the graph data. Now, a lot of time you see this, you won't see, you know, like right now, just now, if I didn't do this, it would say, because there aren't so many entries and it's a sparse array. So the sparse array is collected like this: 1 to 2, points to 1. So this is their internal representation. It's saying that Bob and Jane is 1, meaning Bob knows Jane is 1. So the left side of the bracket is who. The right side of the bracket is whom. Who knows whom? 1 knows 2. Bob knows Jane. Yes, 1. Okay. Now it's called sparse matrix because you can imagine that we can have a matrix of 5,000 by 5,000, and they don't want to keep all the numbers. They just want to keep the ones. That's what sparse matrix means. You just keep the non-zero element, everything else throw away. Okay. But this is hard to see, so I turn it into what's called normal form. Turn it to normal form. Okay. And I put in a matrix format. You get that, right? Okay. But technically, if I just have this, Mathematica will know that, wait a minute, there are 9 numbers. I only need to keep 2. I'm just going to keep 2. Okay. So that's why you see a lot of this kind of and this is very expensive. Matrix can be very large really quickly. Okay, so sparse matrix is the normal way that you would keep. Okay, but if you want to look at it, you can look at it. It's just going to put zeros. Okay, so anyway, this graph, let's do 2 things. Okay, one is a built-in function called find community. So this is a little bit like clustering, except it's not clustering by attributes. Okay, so let me show you an example. Let's say, oh, the example that I used was a dolphin, right? Let's use a dolphin. Well, it's in here somewhere. Okay, where's the dolphin? Yeah, there. Where's my dolphin? Okay, anyway, there's a network of dolphins. Okay. If I take the yeah, I think it's this one. It's just not labeled here, so you can't see. Okay. Dolphin social network. Yeah. There are 62 dolphins together. 62 dolphins. If I take the weight of each dolphin, the length of each dolphin, and the age of each dolphin. Each dolphin has 3 numbers. I can do cluster analysis, right? I can even do list plot. If I have 12 dimensions of dolphins, I can do dimensionality reduction. So this will be like the problem we did earlier, right? So 2 dolphins are close together if their measurements are close together. But that's not how society works. Okay? Tall people like to hang around with short people. Right? That happens all the time. So I don't care if dolphins are close together because they have similar size. I want to see if they swim together. Right? And I want to say clustering based on their swimming. I don't know why the picture does. I think I must have done it here. It's in here somewhere. Well, let's do it from scratch. We can do it from. Okay. Example, right? Example data. I think it's called network graph. Okay, that's good. Network graph. And I think it's called dolphin. Yeah, oh, okay, I have it here. Okay, so this is my example graph. I make it example graph. Oh, there it is. I have to, okay, yeah, that's good example. Okay, let's start here, start a little bit earlier. Okay. There it is. Okay, so example adjacency matrix and then example graph. Okay, and I'm just gonna go really quickly. I don't want this guy. I want dolphin. So let's take example graph. Example graph. Dolphin social network. Ah, there it is. And so this is how different dolphins hang out to each other. But I can do this. Graph, community graph plot. Okay, that is. Basically, this is a quick shot. There. Okay, there. Okay, so right now, if you look at this, by the way, this can all be labeled, right? They have names for all the dolphins. This is how dolphins swim together. You can kind of roughly see that these two kind of hangs out and not very friendly, maybe. And maybe there's some groups here. There's a large group there. There's a smaller group here. But you can't really tell. But if you use unsupervised learning in a way, right? So it was called community graph plot. Ah, you can see there. There's not the two not so friendly dolphins, and there's 3 gangs of dolphins. Okay, so this would find graph community. In other words, community in this sense is cluster. Let's put it this way, okay? The cluster works by attribute, so you would say, similar height, similar weight, tall dolphin with tall dolphin, with fat dolphin, with fat dolphin. But in this case, tall dolphin may like to swim with short dolphin. It's their hangout. So we'll call it not cluster, we'll call it community. Okay, so this is a graph community. And this is also very good for project. And so you can do this. Okay. Now, what if, look at this, and I say, who is really like the center of this network? Then I can do centrality, and I'm not going to repeat the thing. Centrality has many meanings, right? Again, who knows whom, and then centrality is based on who is the most influential sort. Okay. I would like you to think of two concepts. Okay. One is a recursive concept. I am central to this network because I know a lot of people who are central to this network. I am an influencer in this group of friends because I know a lot of people who are influencer. They are influencer because they know a lot of people. Sorry, in influencer, it would be something like I am followed. Okay, let me say that again. So if I have a graph of who follows whom, okay, and I want to target my product, and I want to know the one guy or the two guys that I'm going to spend a lot of money promoting my product on. I'm going to start by saying an influencer is somebody who is followed by a lot of influencers, whom in turn are influencers because they're followed by a lot of influencers. This recursive equation leads to what is called concept of eigenvector centrality. Now, I don't want you to stick to that word because a finer version or more improved parametric version of it is called page rank. And that page rank is so popular, it's what made Google successful. So that recursive one, just remember page rank maybe. Okay? So find the page rank centrality of the Twitter network and then get the one that has the highest score. That's the one I want to promote. On the other hand, what if the communication for the groups of friends, okay? So news from A to go all the way to P has to follow this shortest path. A has to call B, B has to call C, C call F, F call H, H call P, okay? And you find the shortest path, and this might work in a gossip network or a travel network. I want to find what is the most intermediate in the sense that all the shortest path always pass through this guy. So you can take Thailand and 77 provinces, and you say, okay, if a husband lives in one province, wife lives in another province, and they want to see each other by crossing as few provinces as they can, that's the shortest path. Okay? And I do this for 77 times 76 divided by 2 possible combinations. Okay? So 77 times 72, 6, because you don't want to travel to yourself. Divide by 2 because A to B presumably is the same thing as B to A. Right? Calculate those numbers. Calculate those numbers. Those are the shortest path. Then you go to each province and say, how many times did you appear in the travel itinerary? Okay, so how many times does Bangkok or Krung Thep appears when somebody wants to go from Yala, which is in the south, to Mae Hang Son, which is in the north? Okay, so maybe the shortest path can go to Kanchanaburi, I don't know, but I think probably to Bangkok. Okay, so you do this for all the Jangwat. Okay, and basically you just rank by how many times it appears. Now, presumably this gives equal weight, right, to all the pairing. So maybe there aren't that many husband and wife pair that, one lives in Yala, one lives in Mae Hong Son. So maybe you could give some weighting, but that's a little bit too much already. So that concept is called betweenness centrality. Okay. Now, finally, the last thing that I covered in this, at least in this text, is this kind of ownership propagation, and this is basically using matrix to multiply by a few times. To be honest, I'm not gonna pay too much attention to this on the exam, because it's if you're gonna learn graph theory, then something, you know, you learn anyway. By the way, this is a good example of use of ChatGPT. I wanted to create adjacency maps of all the provinces in Thailand. Okay, so I can ask, I can go to Wikipedia page, but that's going to take too long. So what I did was I asked ChatGPT because ChatGPT has read Wikipedia in Thailand, to list them. Unfortunately, it's not all correct, but it was good enough. Why? Because I have a list to start, and I just asked, you know, your friend here at Tamphon to verify. It takes a lot less time to verify whether or not it's correct than it is to type in all the 77 times 76 divided by 2 combination. Okay, so I used ChatGPT as a starting point, but there was some error. There was some error that has to be changed. But anyway, so this is correct now. It's correct now. Right. And finally, so the graph computation. So this network propagation of who owns whom. Again, this is something that came out in real life, by the way, this who owns whom. So if I have, instead of Bob knows Jane, Jane knows Irene, it's company A owns 40% of company B. Company B owns 20% of company C, right? The matrix is going to say A owns 40% of B. But to get to how many percent does A own C through B, you have to use this matrix twice. Basically, matrix multiplied by itself. And then you're going to get 40% times 20%, so that's 8%. Okay, and you can do this as many times as you like. Okay. So we actually did this for a real project in analytics for the Thailand's revenue department, because revenue department, they want companies that are basically joint ownership to be kind of like scrutinized together, right? So even though you have 5 companies, they file separate tax. In a way, the revenue stream can all go to A, because A owns B, B owns C, C owns D, D owns E, E owns F. Okay, so what we did was we have a matrix, and then we multiply by the matrix. So that's graph data in Word at Word. Okay, but that's it. I don't want to go into detail. I just want to mention. So these are real life, guys. These are genuine real problem. So with that, what I want to do is are we doing on time? Okay, we could take 5 minutes break.